grasshoppers. They're actually in Mexico. They serve pan-fried crickets as just bar snack food. You know, they pan-fry crickets and kind of salty, and they put out a little bowl of crickets there to sell more beer, like we do with peanuts and pretzels around here.
How many margaritas?
And then, huh?
After how many margaritas?
No, that's right from the start. My Mexican hosts were all excited to take me there and have me get all squeamish. And I said, oh, I'll try that. And I tried a couple, and they taste just like beer nuts or something, but the legs are a little weird. You know, you get a little one of those. Yeah, you get a little one of those. And then in another restaurant they had grass peppers. That's the translation of it. Somebody helped them with that. Instead of grasshoppers, they became grass peppers. But they were just like they did it just like jalapeno poppers. You know, they just deep fried them with grasshopper and
You ate it deep fried.
yeah, you need anything deep fried. Clearly. All right, so let's see. We're working on this business now of finding the center of mass of, well, we were doing it for distributed loads, so we can handle a couple things now that aren't too difficult. You can imagine having a distributed load that perfectly fits some model. Well, we can do that, and it's very good for modeling the weight of the beam, if that's of consideration. And it certainly must be. You know, these beams aren't insignificant in their own weight. So even if we had like a carport or something and we wanted to model its weight, but there are other things that we could also model. Maybe you've got some stuff stacked there. Maybe we want to model it with a linear function. Even if the load doesn't look just like that, it might be close enough for our purposes that it could suffice. Or using the example we had last week and may have here in a couple days of wind-blown load. You know, a bunch of snow blown up against the side of the building would probably look something like that. So even if our load doesn't really look like those things, we can still use our model, use some approximation of that, and then we could find wherever the equivalent load is, and so we could take out the distributed load, put in that equivalent load at the right spot, and we get the same reactions that we would have with the distributed load. So that was the purpose of what we started last week. Is that how you saw it? That was our point. So we were working on that. We were essentially treating these different distributions as solids themselves. We looked at them for the most part, or at least the pictures that are in the book that we can now use as tables are ones of constant density. We did a problem where the density wasn't constant. Well, we did. Alan doesn't know why we did that because it was out of focus. That's what we were doing.
Go under the water.
Well, you might, if you go to get the Ethiopian subtitles, that might help. Yeah.
No, it was not Ethiopian.
But the ones that I showed you, that table in the book that's got a bunch of regular solids in it. For us to use most of those, is treating each of those as constant density. Also, constant thickness. That means thickness into the board. All that's saying really is that most of our problems are 2D problems, which is essentially what we mean when we say we're doing planar solids for the most part. So we were looking at several of those, and that allowed us to place then find the location of the centroid. And I was just using a little bar over it to mark that as the location of the centroid. Once we could place that, then we could find the reactions using that single equivalent force that replaced the distributed force that we couldn't solve directly. We had to solve it sort of indirectly by finding this equivalent force and putting it in the right spot. Remember what that looked like? For the most part, it looked like an integral over the area, which usually was just a matter of us integrating in the x direction. I guess I could just make it look that way. And then over the total area, and that W as a function of x is the load curve. That's the actual functional geometric algebraic shape of whatever curve it is that we're using to model our distributed load. That's what this WX thing is. The load W as a function of x. And so that's what we worked out on Friday. And if we needed to, we could find the location in the y direction as well. If we had the two of them, then what we've got is the actual location of the center of gravity. And it's much the same thing there. A lot of times it can be done as a function of x, as were several examples in the book. So you don't necessarily need the load curve as a function of y. And you did that with integrals.
There's going to be an h at the top of that integral, right? H to 0.
Yeah, if it was run in that direction. Because most of these are constant density, constant thickness problems, then this becomes even simpler for us and allows us to do many other type shapes. For example, if we were looking at a load curve of some kind that isn't easily modeled as a single function, maybe we are specifically looking at a beam in a building, and we know that we're going to have some heavy equipment over here, and maybe some other shapes over there, and even the possibility that we've got all kinds of different possible ways that we might need to model a distributed load that aren't just single nice little things that are in the back of the book. You look in the back of the book, you're not going to find that shape there. You might say, well, maybe we can model it, we can find some curve that will approximate it, and maybe that would be good enough, and then we could do these integrals. But we're not even going to need to do that. What we can do is break this into a bunch of very regular shapes that we can handle, and then look at the contribution of each one of them individually. If we break that into a bunch of rectangles, you already know where the center of mass of a constant density, constant thickness rectangle is. It's right in the center. So we could have one little bit of load there. We've got a couple other rectangles here. And so each one of them has a contribution right from its own center. And then triangles. Anybody know offhand where the center of gravity of triangular shapes is? Well, if you did the integral of this nice linear function, it turns out it's always 1/3 of the way across the base. So it's pretty easy to put those too. So if we divide that into thirds. So we've got each shape there that contributes a little bit to the load. And we could do the problem like that. We did problems where we found the reactions when there were multiple single point loads. So we could take a complex shape like that, break it into a bunch of little pieces, find out where each one of the pieces contributes its little contribution to the total, and we could do them all from there. But it turns out we can also find the center of gravity of the entire shape as a whole by adding them all up, however many there are. Maybe I equals 1 to n. In that case, I did 1, 2, 3, 4, 5. I just happened to draw 6 shapes there. Each shape and the area moment arm, since these are all constant density, constant thickness things, then the density divides out top and bottom, and gravity itself divides out top and bottom, which kind of makes sense. The center of gravity is going to be in the same place no matter what planet you live on. Where you do your homework, I don't know where you go for the weekend to do your homework, some home planet somewhere. Doesn't matter what gravity is there, you'll get the same location of the center of mass that I will as a resident of planet Earth. And we divide that by the total area. That's the total weight after anything else divides out, the density and g. Then all we're left with when we're doing constant density, constant thickness, planar solids, is we just have to look at the area of the shape itself. And we don't have to deal with any other part of it. And we could do the same thing in the y direction. And we can do all kinds of complex shapes. All right, so let's do a couple, and it comes out to be fairly straightforward for us. So we just need. The other thing is the reason we need to find the y coordinate of the centroid is not really for any of these problems. All these problems depend upon is the x coordinate because gravity is in the y direction. However, we're going to have other complex shapes like cross sections of beams coming in next term in the 209 class that follows this one, and we're going to need to know where the centroid of these, the area centroid of these shapes is. Since it's a little heavier up there, you'd expect it to be kind of near the top. So we're going to need to find both the x-coordinate and the y-coordinate to locate the centroid very specifically of many of the shapes we have coming up in the follow-on course here, 209. So we're going to do a couple of these practice parts here where we find both the x and the y location. It's the same steps to find either one, so it actually comes out to be quite easy. So imagine we have this shape. And we want to find the centroid of that, the location of the center of mass of it, both in the x and the y direction. Give it a couple dimensions. 1 foot, 1 foot, 2 foots, 2 foots across there too, and then little bit. Well, let me just slope that out a little bit extra so it looks a little better. And so that's 3 feet on either side there. So something like that. So that's our, maybe a distributed load, or it could even be the cross section of a beam we want to use. God knows why you want to use a beam that looks like that, but all right. And we want to find the location of the centroid of that. Now there's a couple different ways to do it. I'm going to do it in a particular way that might not have been the way to have done it based on what I just talked about with that one, but it will illustrate what we can do for all kinds of other complex solids. So first thing we want to do is arbitrarily locate a system of axes. Just establish a place from which we measure everything. We just need that for reference to find out where the centroid is. Then once we found out the centroid, it's pinned to the solid itself and we don't need these axes anymore. It's just a place to start measuring from. So I can pick anything arbitrarily. I'll go ahead and pick that. And then once we find the location of the centroid with respect to that axis system, we don't need that axis system anymore because we know where the centroid is, and that's a characteristic of the solid itself. All right, so that's our first step, and it's arbitrary where we put it. You could put it anywhere you want. That's not going to change the location of the centroid once we find it. It's going to be wherever the piece is, and its shapes determine where the centroid should be. Then we break our shape into regular solids, regular shapes, whose centroid we can find with almost no work. Maybe you have to look it up in the table, but you don't have to do the integration. You don't have to do a bunch of work. Just find a bunch of little equivalent shapes that we can make this. Actually, I don't think I'll do it that way. Let me do it this way. I'll just number the shapes there. And again, it's arbitrary what we choose. So just for reference, I'll number that one 1. Remember, we have to do I to N for however many shapes we've got. I have 6 in my silly little example over there. So it's however many shapes we break this into. 2. Now, you might not see it this way. You might think, well, let's make this one 2 and this little shape here 3. But I want to illustrate another way to do it to get the very same thing. So 2 is going to be this entire square with a corner taken out of it. So I can show you how to handle shapes that are missing part. For example, what if this was some kind of shape, but right in the middle of it we had an empty tank or a conduit or something, and so that wasn't contributing anything to the load. How do we handle that? And then this little square itself will be shape 3. So I've got 1, 2, and a little piece of 3. And again, you could do this by making it 1, 2 would be the tall rectangle, 3 would be the small rectangle. You could do it that way and you get the same thing. In fact, it'd take you just a few minutes to test this. All right, what we're looking for, remember, is the location of the center of mass by finding where each little piece has its center of mass. And since these are planar constant thickness solids, their center of mass is the same place as the centroid of the shape itself, the area centroid. So the easiest way to do it is to make a little table. We've got 3 pieces, so I is going to be 1, 2, and 3. For each one of the pieces, we need to know where its centroid is with respect to our reference axes, which are arbitrarily chosen. So we'll need xi for every one of them. We'll need the area of every one of these 3 pieces. So I'll put that in the table too. And then I need the product of those 2. And sum of that column will be the top, the numerator. And then I want to do the same thing in the y direction. So I'll also need the location of the centroid in the y direction and the product of yi, ai as well. So let's just step through that. Piece 1, a triangular shape. I'll give you 30 seconds and you can do the integral and find out where its centroid is. Or you can look in the book, remember in the appendix, Appendix D I think it is. And I see it. It's right here. There it is. All right, we're lucky enough to have a right triangle. And so if you go through the location of x bar with a right triangle, which means A and B are the same, you know that then it says that it's 1/3 of the way along the base. And it looks like 1/3. With respect to our reference axes, so x1 will be 1/3 of the, will be just 1 foot. Its area, 1/2 the base times the height, 4.5. All right, so that's foots squared, 4.5. X times A is 4.5, and that's feet cubed. That, remember, is the that comes from the moment arm of that little piece, but its density and G all divide out top and bottom, so that's why we're just down to the area when we're using constant density, constant thickness, planar solids like we're doing. The location in the y direction of the center of mass, it's also 1/3 of the way across, and so that's also 1. And so YI, the A is the same, we don't need to redo that. And that's all you do. We do it for the other shapes. 2 2 is this 3 by 3 square we've got here. Even though there's a little chunk taken out of it, we're going to handle that in a second. Its centroid is what? Negative 1.5. We have to account for the fact that it's on the other side of our reference. It's arbitrary where we picked that, but we have to account for that. Its area is 9. 9 times negative 1.5 is negative 13.5. So you do, what's yi for that shape? With respect to our arbitrarily chosen reference system. What's yi? It's just a square. It's just the middle. We go halfway up, 1.5 in the y direction. And a is the same. There's not a negative on either one of these, so this is plus 13.5. Now those don't cancel because they're each of parts of a separate calculation. They're not in the same calculation. Because one we use to calculate the x direction, one we use to calculate the y direction. Now, here's what we do for the piece now that is actually a missing piece, because it's a chunk taken out of our regular solid. Here's how we handle it. X we handle in the regular way. Let's see, it's in the middle. It's 2 feet out, and then another half a foot in the negative direction. It's minus 2.5. Sound right? That's the location of its centroid, the individual centroid of the individual piece. Its area is 1 by 2 square feet. However, it's a missing piece, so we give it negative area, minus 2.0. That's how we handle any part that's missing from our solid. We just give it a negative area, or a negative mass, if you will. Since remember, the mass is all cancel out. So multiply those, that becomes plus 5.0. And y, its centroidal location is 1 foot up and then a half a foot up, 1.5.
Wait, would it be 2? Because it's 2 feet.
Oh yeah, that's 2 feet. So half of that. So yeah, it's 1 foot plus another 1 foot is 2 foots. And then times that negative area is minus 4. All right, and we need the sum of the x times a column. So we need the sum of that column. And we need the sum of the area column itself. So we need the sum of that column as well. So whatever those come out to be. I think the area is 11.5, is that right? And we need the minus signs because it tells us which direction we're in. And what's this one come out to be? 9.5, negative 4. And so X bar is that column over, and notice that's feet cubed, and this column is 11.5. It's feet squared, so the units come out right. And you get what? Negative negative 0.35. Negative 0.35. And the negative is important because it tells us we're on the left of the coordinate system we picked. So maybe about there, give or take a little bit, which makes sense. You can look at that picture and tell, yeah, it's going to be a little bit heavy to the left side from the axis line I picked, because there's a bigger chunk missing over here than is missing over here. So it is going to be a little bit heavy to the left side. And then we can also figure out what it is in the y direction. Y bar equals whatever the sum of that column is. 14 divided by the sum of the area, which we've already got, the 11.5. And the units are units of distance, because we're placing a position here. What's that, about 1.2? 1.22, something like that? Feet, 1.22 feet. And so we're up not quite halfway, which is about what you'd expect, because there's a bunch of stuff near the top that's missing. So be a little bit. And so there's the centroid, the center of mass. If we cut this out of a sheet of plywood, that would be the center of mass right there. If we're modeling this as a constant density distributed load, we certainly want the x bar distance. We wouldn't need the y bar distance, but we're going to need that for later terms, for spring term anyway, so that's why we're going to work on the same thing at the same time. And usually you can look at the solid and say, yeah, that's about where it looks like it should be. It should be a little bit to the left and not up at halfway, because there's a bunch of pieces at the top missing, so that's going to pull the weight down a little bit. So you can usually look at your shapes and see if your number makes sense. And so we know the center of mass is something like that, about where you'd expect it, give or take a little bit. And you could have done the same thing by breaking it into that shape and that shape and that shape. You would have gotten the same thing. And you can try that. Actually, it only changes. It changes these two a little bit, just because you've got different shapes to them. So I think the easiest way to do it is by making a table of the solids rather than trying to run these sums as you go along. If you make a table, it's just a lot less chance of making a mistake. If you ended up placing the centroid over here somewhere, it's really easy to check if you missed a minus sign or something on one of those. Remember, the minus signs on this was with respect to our reference frame, and the minus sign here was because of the negative, the missing area. now that we know where it is, see, we don't need the reference frame anymore because we know just where the solid, we pin it right to the solid, and we don't need that reference axes anymore. Okay, ready for one of your own? Yes, sir. And there's several in the book that you're going to do. Some of them I think are even 3D or quadri 3D, which means they're symmetric in one direction. Okay, here's a piece for you. Big T shape there. Comes down about as far as it is wide, because this is 150 millimeters across the top and 150 millimeters down. All right, so all the dimensions here will be millimeters. Millimeter web there, and then there's a circular shape down here at the bottom, radius 50. There. Yep. Alright, so I want you to find the center of gravity of that. This is the type of thing we're going to need to do next term when we look at the cross-section of beams, and we need to know where the area centroid of all the beams are. As long as you have the numbers right, it doesn't matter so much what the picture is. Okay, remember your first step? First step is locate a reference axis. Anywhere you choose is fine, because at the end you're going to get the same number hopefully as anybody else, so it doesn't matter where you put it. When I do it all, I have to pick one in particular, but we can use any one we want. Make your table kind of big here if you're going to deal in millimeters, because these numbers get real big. We've got these dimensions actually cubed a couple times. You could do the upper part as a big square missing two little rectangles on either side, but it might be easier just to break it into the top part of the T and the, whatever they call it, the trunk of the T. Of course. 'Cause there's some round off anyway. Now we need to know where this is within maybe a millimeter or something. Place a reference system somewhere, it doesn't matter where. You can do it with the top edge, you can do it with the bottom edge, you can do it with the middle of the circle, you can do it anywhere you want, it doesn't matter. Hopefully it makes sense putting the y-axis right down the middle. Why? Because it's symmetric. So I already know where X bar is. You don't have to do that one. Now by looking at it, since it's symmetric, X bar is right down the middle. So that'll make X bar 0. You don't have to do it. We've already started doing it. Made a column for it, but you then realize the folly of what you're doing. Alan has this column of zeros. Looks like most everybody picked the obvious division into 3 solids. We don't need to do X bar, we only need Y bar. And you know, well, maybe it's not obvious whether it's going to lay halfway up or closer to the top, closer to the bottom. But you know it's going to be somewhere reasonably in the middle there. That just makes sense. Imagine this was cut out where it would balance. And you can change it to meters if you want. The numbers don't get quite as big. Doesn't matter. We're just trying to locate the thing. Think you got it? Well, that doesn't help me any. I don't know where your reference. Oh, your reference is from the center of the circle. Okay. You can pick your reference from anywhere. Once you locate it on the solid, you don't need that reference system anyway, so it doesn't matter. Do it from the center of the circle. Fine, no trouble.
You did it from the sides?
Oh, you got some green, that sucks. if you have the origin somewhere in the center, it can make some negative signs is all. So, for example, I'll just put it along the top edge, count down as positive.
It's 200.
What most of you do? The center circle?
7.5 to 70.
You did center circle. You did center circle. Bill, you did bottom of the circle. Mr. Rex?
Yeah.
Where's yours? Bottom of the top. Oh, you did your center circle too? Okay, we'll pick center of the circle. So we can get all the same numbers. Doesn't matter. Oops, I put it in blue. That sucks. Alright. The location of the centroid of the first top piece from the center of the circle. So we go up 50, up another 150, that's 200, plus half of what's left over. And we go to the midline of that top bar. So that's 207.5. Is that right? And that's millimeters. 2 is up 50, up 75, 125. And then that one's 0. Is that right? The area, what's the area of that circle? Pi r squared? Who has it? 7854? Sound about right? That's the circle, 7854. 15 times 150, and they're both the same shape, 2250. And that's millimeters squared. And then those things multiplied. Is that right so far? You got those same numbers? For those of you who did it from the center circle? If you did it somewhere else, you're going to have slightly different numbers, but in the end, we'll get the same answer. So, the product of those two. 466, 875. Product of the next two. 281, 250, and product of the last one is 0. So we need the sum of that column, that's millimeters cubed, and we need the sum of this column. So sum of the area column, 1, 2, 3, 5, 4. Is that right? That should be the same for everybody. And then the sum of your YA column. 748. 125. Sound right? I'm trusting Alan on them because I had a different reference point, so my numbers will be slightly different. So, God forbid, I'm trusting Alan on those.
I do have a calculator, so.
Yeah. I know what that means. And the units come out right. Well, millimeters cubed divided by millimeters. And that comes out to be
60.56.
60.6.
Oh, well, now.
And that puts it a little bit outside of the circle. So maybe about there. Now, next term, we're going to need that location because it's going to turn out that that's something we're going to call the neutral axis. And so we'll need that point. For this term, we need to find the centroid so that we can locate distributed loads with the equivalent load. But next term, we're going to also need that as the neutral axis.